All right, welcome to section 1.6. In this section, we're going to be focusing a little bit more on integrals involving exponentials and logs. There isn't going to be a lot of new content for us here. Instead, we're just going to get some practice with the methods, especially that of substitution, that we've learned so far in order to compute some integrals involving exponentials and logs. So the first thing that we're going to do is compare kind of the difference between the power rule and the exponential rule. So for instance, example 1 here is asking us to compute the integral of x squared dx. This is our power rule for integrals. In particular, we notice the way that we can differentiate or distinguish between the power rule and the exponential rule is whether or not we have the variable to a number or a number to the variable. In this case, we recognize x squared is the variable raised to a number power. And that's going to indicate to us that we should use the power rule. So the fact that we're using the power rule here, we know to increase the exponent by 1, so we go up to x cubed. We know to divide by the new exponent, so we're dividing by 3, and we always add c. In contrast, for example 2, what we're looking at here is the function 2 to the x. This, instead of being variable to a number, is number to a variable. And because derivatives treat these two situations very differently, so do integrals. So we're going to have to do some kind of have some kind of different strategy here. The strategy that we're going to employ for this one is that we know how to take the integral when it's e to some power. We know what the integral of e to the x is, for instance. So I want to rewrite this in terms of e's and using e as the base of my exponent. In order to do that, I'm going to think about rewriting the number 2 in kind of a funny way, but it's going to be a helpful way for the purpose of doing this integral. I'm going to rewrite 2 as e to the natural log of 2. I'm taking advantage of the fact that the exponential and logarithm are inverse functions here. So if I use this rewritten form of 2 in the integral, I can say, well, this is e to the natural log of 2, all raised to the x power. And then one of my exponent rules says if I have repeated exponentiation, so if I've got something to a power to another power, I can multiply these two powers. So here I have the integral of e to the natural log of 2 times x dx. But this looks very similar to some of the u substitution integrals that we've been doing. In particular, if I let u equal natural log of 2 times x, what I will have in my integrand is e to the u, which is a very nice function. We know how to integrate that. So let's think about what du is. Du dx is going to be natural log of 2, because this natural log of 2 times x, this is a linear function. Even though it has a funny looking coefficient, natural log of 2 is just a number. So the derivative of u with respect to x is the natural log of 2. And that's going to tell me that du equals natural log of 2 dx, or rewritten, du over natural log of 2 equals dx. So when I'm going through and I can do this substitution here, I have the integral of e to the u, since I've set u to be natural log of 2 times x, and then I'm going to replace dx by du over natural log 2. Since natural log of 2 is a constant multiple, it's going to stick around in this integral procedure, and we're going to here get e to the u over natural log 2 plus c as the integral, which we can then rewrite as e to the, let's see, we had u being natural log of 2 times x, all divided by natural log of 2 plus c. Continuing on, this is certainly a fine answer, what we have right here, but maybe it would be better if we were to write it a little bit more simply. In particular, we notice that this e to the natural log of 2x here Well, e to the natural log 2x was exactly 2 to the x. So we can reverse all of the steps that we did previously to rewrite this as 2 to the x over natural log of 2 plus c. So in the end, we get kind of a nice antiderivative here in the sense that we started with integrating 2 to the x. We ended with an antiderivative in terms of 2 to the x, but we have this additional factor of natural log of 2 here. So it's important to keep track of that if we're working with integrals of exponential functions whose bases aren't e. When the base of the exponential is e, this factor isn't present, but for other bases of exponentials it is. More generally, if we have some constant number a here, we can compute the integral of a to the x. And the process works very similarly to how it did with a equals 2. So we're going to take advantage of the fact that we can rewrite a as e to the natural log of a. Then that power of x is going to get multiplied by natural log of a there, dx. We'll be able to use the same u substitution that we did earlier. We'll have u equal to natural log of a times x, and then du dx. Well, we can do the exact same procedure again. We'll get du over natural log of a equals dx. Then we'll have that this integral is integral of e to the u du over natural log of a. Continuing on, we will get that this is e to the u over natural log of a plus c. And then again, using the same tricks that we did with a equals 2, we'll find that this is a to the x over natural log of a plus c. So for the particular case where a equals e, as I was talking about earlier, we'll have e to the x over natural log of e, but natural log of e is just 1. So this formula agrees with what we already know about the integral of e to the x. But now we have a nice, more general formula for the integral of any base that we like for our integrand. All right, so that's one helpful trick that we have with exponentials. When we have bases that aren't e, we can rewrite them in terms of e's in order to actually do an integral. So what are some other tricks that we have? Well, it's really nice to take advantage of the fact that e to the x is its own derivative when doing some of these integral computations. So for instance, here when we're asked to find the integral of e to the x times the square root of 1 plus e to the x, we can, when we're doing u substitution, we know that we want to pick u to be some function whose derivative is floating around in the integrand. So if I pick u to be this 1 plus e to the x here, then the derivative of that will be e to the x, which is floating around in the integrand. So let's see this process play out. I'm going to take u equals 1 plus e to the x, so that du dx is e to the x, i.e. du is e to the x dx. So now when I am going through this integral and I'm doing my substitution, I know that this 1 plus e to the x under the square root is a u, and I know that the remainder of the integrand, this e to the x dx, I can replace that with a du. And now we have this nice integral that we know how to take, because this is the integral of u to the 1/2 du. Now we recognize this is variable to a power. So variable to a power means apply our power rule. So increase the exponent by 1 and divide by the new exponent plus c. Going back and replacing our u's in terms of its expression in terms of x, we know that u is 1 plus e to the x. And dividing by 3/2 is the same as multiplying by 2/3. And we have plus c. So kind of nice to have the fact that e to the x is its own derivative in order to do this sort of integral computation. Example 5, we have a word problem here. We are looking at the number of black-footed ferrets in a population t years after 2020, and it can be modeled by the equation f of t equals 87 e to the t over 1 plus e to the t. We want to find the average number of black-footed ferrets in the population between 2022 and 2024. So we have if we want to find an average, we know that we have a formula which is going to describe how to find that average. The formula says integrate the function that you want to compute the average of. So in this case, we have f(av) equals the integral of 87 over 1 plus e to the t, 87 e to the t over 1 plus e to the t dt. We want to also, this had better be a definite integral in order to get a number out. We want to, if we're integrating, we want to think about what the t values of these years correspond to. 2022 is 2 years after 2020, so that's going to correspond to t equals 2. 2024 will correspond to t equals 4. And since we're finding the average number of black-footed ferrets in this interval between 2 and 4, we want to integrate from 2 to 4. And out front, we need to have this factor of 1 over 4 minus 2. 1 over the upper limit of integration minus the lower limit of integration. So all this together, now we need to actually do this integral now that we've got the setup down. So as with the previous example, we maybe want to recognize that I've got this e to the t dt here, and that is the derivative of the denominator here, of this 1 plus e to the t. So I want to let u equal 1 plus e to the t, so that du dt is e to the t, and du is e to the t dt. Continuing on, we're going to actually do our substitution here. So this is going to be that 1 over 4 minus 2 is a factor of 1/2. I can also factor an 87 out of the integrand because that's not doing very much there. So we're left with integral from t equals 2 to t equals 4 of, let's see, that e to the t dt in the numerator we are going to replace with a du. In the denominator, we have that 1 plus e to the t, and that's what we're going to replace with u. So this is the integral of 1 over u du. And now we know what the integral of 1 over u is. It is the natural log of the absolute value of u. And we're evaluating from t equals 2 to t equals 4. In order to actually do this evaluation, we need to get our integrand back in terms of t, or we need to get I suppose, our antiderivative, which is what we have now. We need to get that back in terms of t. So we have 87 over 2 here, natural log of the absolute value of 1 plus e to the t, and we're evaluating this from t equals 2 to t equals 4. And if you go through and you actually plug in these numbers and plug it into your calculator, you get that the answer here is around 82.3 ferrets. So here we're able to find out that on average, between these 2 years, this population had 82.3 ferrets in it. All right, last example problem for this section. We want to compute the integral of natural log of absolute value of x divided by x dx. So this is a common type of problem where we have some integrand involving a natural log. And whenever we have an integrand involving a natural log, we want to keep an eye out to see if there's a denominator of x. The reason for this is we know that we don't know how to take the integral of functions involving a natural log. So we really want to get rid of the natural log in some sense when we are computing this integral. And the way that we get rid of the natural log is we're going to let u equal natural log of absolute value of x. When we do this, we're really hoping that we have an x in the denominator because we want the derivative of u with respect to x, which is 1 over x. We want to be able to use the fact that du here is 1 over x dx in order to get rid of all of the x's in my integrand. So in this case, it turns out we have this 1 over x dx thing here, which is going to allow me to get rid of the x's. And so what we have here is that this is the integral. I'm going to replace natural log of absolute value of x by u. I'm going to replace 1 over x dx with du. And again, we're left with a fairly simple integral here. We now can integrate u. We know that the integral of u is u squared over 2 plus c. And we can replace u by its definition of natural log of absolute value of x. So we have this thing squared plus c to complete this integral. So maybe the best thing that I can say right now is that the most helpful thing for you to do is for you to do a lot of practice problems involving integrals, both with exponentials and natural logs. There's only so much value that you can get out of watching me do integrals. So go do lots of practice problems and see what you can figure out. You know, not every u substitution strategy is going to be the same. Make some mistakes, do some right things, because those are the ways that you're really going to learn how to do these integrals. Again, watching me a lot is only going to get you so far. But actually taking the time to do practice problems is going to benefit you a lot more.